for joining the 6th virtual panel from CAD for Assurance initiative on hardware security and trust. That's the topic we are focusing in CAD for Assurance. Thank you for joining. Good morning, good evening, good afternoon, wherever you are on the earth. We have an exciting panel today, and we are joined by two truly distinguished set of panelists, which of course our moderators will introduce. And of course, we are very privileged to have two wonderful moderators with us. We'll talk about that panel today, but before that, I wanted to give you a quick overview about the CAD for Assurance initiative. I'm Dr. Saurabh Punia from University of Florida. This particular initiative, which again we call CAD for Assurance, was launched October 2020 by members of the hardware security community. And when I say members, we did involve more than 70 contributors right now, contributing different EDA tools. These are mostly academic tools that came out from the hardware security research. These tools and the corresponding benchmarks as well as publications are uploaded and shared with the broader community through the CAD for Assurance web portal. And if you have not visited that, of course, I will strongly encourage you to visit. Right now, there are 56 different CAD tools. You are welcome to upload your CAD tool if you like to share with the broader community. Again, these are academic tools. Right now, we are not sharing industry tools. Of course, those are already probably known to the broader audience. We have over 3,000 benchmarks in the website. That list is growing. If you would like to use benchmarks on hardware security, ranging from benchmarks in hardware Trojan, locking, obfuscation, side channel, you should have those available in the website. We have right now about 12,000 users. This is the Google Analytics report I downloaded a few minutes before this panel. We have, as you can see, about 12,000 users, unique visitors, and users of the portal, as well as about 38,000 page views. So that's definitely pretty impressive, given the size of the hardware security community, as you are all aware. We have organized as part of this initiative 16 tool demos and webinars in last 2.5 years. We started during the peak of pandemic, but we want to continue post-pandemic, and of course, we need your help to do that. We also have one course webinar and 5 virtual panels. This is the 6th one in the panels, which have been very popular. We have received a large number of attendees, more than 1,500 registrations, and more than 1,200 attendees in these panels, which we have already received. And of course, we want to continue that momentum. We are co-sponsored by IEEE CEDA, HSTTC, that's the Hardware Security Technical Council, and several industry partners who are our technical sponsors. Definitely, we are grateful for their support. And the organizing committee includes myself, Professor Gang Ku, who is also in the panel today, Professor Sung Yi Ho, and Professor Ye Jin. Well, I will not take much time. I will hand over to you, Dr. Ye Jin, and then he will introduce the moderators. Before we hand over to the moderators, we are again grateful to all our technical sponsors, particularly IEEE CEDA and HSTTC, who are organizing these webinars. We solicit your participation in any role you like. You can upload your tools in the website. You can offer to present webinars on the tool, and you are also welcome to organize and participate in the panels. This is just a quick snapshot on the 5th panel we had a few months ago. By the way, all these panels and tool demos are recorded except for one and uploaded in the CEDA CAD for Assurance website. If you type CEDA CAD for Assurance in Google, you will be able to come to that website, and the recordings are available. So if you have missed any of these panels or webinars, I will encourage you to visit the website and look at the recorded videos. And of course, today's panel also will be recorded and posted in a couple of weeks. With that, I will hand over to Dr. Ye Jin to introduce the moderators.
Thanks, Roop. Thanks everyone for joining. So it's my great pleasure to introduce our 2 moderators, since they are already well known in hardware security, in the hardware security community. So I will keep my introduction very short. So we have 2 moderators, Domenic Forte from University of Florida and Qiaoyan from University of New Hampshire. So, as I mentioned, these two moderators are very well known in hardware security community, so I will leave the podium to them.
Thank you, Domenic and Qiaoyan.
Okay, yeah. I can briefly introduce this panel. Thank you everyone to attending this panel. So for the past decade and a half, the Hardware Security Committee has dedicated significant time and attention towards the threats related to semiconductor globalization. With the passage of the CHIP Act in the US and similar in Europe, it's a time to reconsider the intellectual property protection and assure in the new context. For example, physical attacks in parallel with chip design and computing landscape are shifting in order to compensate for the losses in energy efficiency, performance, and etc. So on this panel, we discuss the recent trends, debate their positive and negative impacts on hardware security, and forecast the new frontiers to be explored by the hardware community. With that, I will let Domenic introduce the panelists and we'll start the conversation. Thank you.
Hey, thanks, Qiaoyan. Thanks, Forte. Thanks, Year. And thanks, everybody, for joining. So I'll introduce our first speaker, Serge Leef. He received his BS degree in electrical engineering and MS degree in computer science from ASU. He has served on corporate, state, and academic advisory boards, delivered numerous public speeches, and holds patents in hardware Trojan and Internet of Things infrastructure. Serge joined Microsoft's Azure business in March 2022 to pursue the vision of cloud-based secure microelectronic design, implementation, and fabrication enablement. And previously, Serge spent time at Microchip, Intel, Silicon Graphics, Mentor Graphics, and most recently, DARPA. Qiaoyan, you want to introduce the next speaker?
Yeah. David Kehlet earned a bachelor's degree and a master's in electrical engineering degrees from Stanford University. He is a researcher at Intel working on pathfinding for programmable logic technologies. David is currently developing chiplet technology and is a PI of the US government's state-of-the-art heterogeneous integrated packaging chiplet design technologies project. Earlier at Intel, David was vice president of IP engineering. Domenic?
Yeah, it's my pleasure to also introduce Murthi Sadhasivan, who has a dual master's degree in computer science and computer engineering. He has over 30 years of experience at Intel Corporation as a hardware design engineering lead and architect, with 10 of those years with experience as a security hardware engineering lead and digital rights management designs. He's also spent time at various startups, but his current affiliation is Senior Engineer Specialist at the Aerospace Corporation. He's most interested these days in anti-reverse engineering methods for silicon and board design, deployed operational mode hardware Trojan detections and mitigations, and new IoT-centric cryptographic solutions. Qiaoyan?
Yeah, next one will be Gangqi. He received his master and PhD degrees in computer science from UCLA in 1998 and 2000. He joined the ECE department at the University of Maryland in 2000, where he also holds a joint appointment with the Institute for Systems Research. Dr. Qi works on power, energy efficiency, and security problems in the design of integrated circuits, embedded systems, cyber physical systems, and the Internet of Things. Dr. Qi is currently serving as a term in NSF program, but today he's here in his capacity as a University of Maryland professor. And the last panelist will be Chang. He's a professor of the School of Electrical Engineering, Electrical and Electronics Engineering of Nanyang Technological University, Singapore. His current research interests including hardware security, AI security, biometric security, trustworthy sensing and hardware accelerator for post-quantum crypto and edge computational intelligence. That's all about our panelists. Yeah, Domenic?
Okay, so we could start with the positional statements from our panelists. Then we'll move on to some initial questions from the moderators, and finally questions from the audience and closing statements. So we'll go in order of introduction. So Serge, can you share your screen and give the first position statement?
Domenic, I am not allowed to share my screen right now. Somebody needs to allow me to do that.
Okay, can you try again?
Indeed, yes. Thank you. So hopefully everybody can see this. Per introduction, I recently spent 4 years at DARPA, and basically majority of the security programs was under me during my term. And so I thought I'd just give you a 3-minute tour of the security activities that that I oversaw when I was at DARPA, and tried to push state of the art in that space. And so there was considerable investment ongoing, and a portion of my portfolio was focused entirely on security. Even some of the programs listed here, not in the security category, like Sahara, had a huge security component to it. So to start with, there was a program called SHIELD. In this program, we created effectively a tiny chip. And this chip contained crypto, intrusion sensors, and fragility mechanisms that would eliminate the odds of its removal. And it was supposed to be glued or attached into the package of the chip and establish unique identity characteristics that could be probed. And so the capabilities here were basically enrollment and authentication, and the goal was to secure the supply chain. Then the next program was ACE, and in ACE, what we tried to do is to automate inclusion of scalable defenses into chip designs, recognizing that different types of chips warranted different levels of investment in security. What we did in ACE is essentially combined 3 things. We established on-chip structures that were unified under the umbrella name of Security Engine that was involved in security policy enforcement, monitoring, provisioning, and authentication. We also created a number of chip assembly tools that were platform-centric and put together an entire design while weaving the security into the architectural plumbing of the chip. And then there was a group of tools also that could be used during the design process to create obfuscated, watermarked portions, as well as simulate attacks and analyze threats. And the idea was that the designer could specify power, performance, and security goals, and the system would go through the optimization sequences and created plausible architectures to meet the constraints specified by the designer. We also had a program on security GRC. This was actually involving University of Florida, and the idea was to establish a set of rules applicable at RTL, netlist, and layout levels, and to be able to apply those design rules or security rules during the design process to attempt to identify and potentially eliminate most obvious and known security vulnerabilities. Another program called SCATE focused on simulating side channel attacks and fault injection attacks, and in essence attempted to, in software, replicate the type of attack vectors that are currently common in labs. So the idea was to essentially replicate in an overnight simulation the same kind of results that today's hackers, or professional hackers, if you will, take about 6 weeks to do, to assess vulnerabilities, to extract keys and stuff like that. And presumably, if you can do that so rapidly, you can make changes in the design that prevent this type of attacks post-silicon. And last one, this is a kind of a whale that got away from me. This is a program I really wanted to do, but as some of you may know, DARPA's service is term limited. And so my terms, I served 2 terms and my term ran out before I was able to execute this program. But the idea was to analyze the layout to observe where are the vulnerabilities present for optical probing and fault injection. And so we know that those things are possible. The question is, can you arrange the layout in a way that resists it? And so the idea was to identify a security asset in the logical representation of the design, observe how this logical structure was ultimately realized during place and route, and how the security asset turned into a chain of polygons. And then to observe like what segments of those chains could be accessible directly to light from above or below, or could be reachable by fib through drilling through structures that maybe do not exist above or below, or they're non-critical. And so, you know, there was a certain worldview that was developed that you know, so what is detection? You know, detection is assessment of accessibility of individual polygons, and you know, then you can characterize this detect accessibility with the direction, angle of attack, degree of invasiveness, and you know, what are you trying to do? Read data from this thing or write? And then we also looked at mitigation. In other words, how do you rearrange the polygons to resist this kind of attacks? Do you insert blocking shapes? Do you stretch, move surrounding polygons, kind of like what we do in OPC, in order to make attacks more difficult? Or do you actually reroute the whole system with a new updated set of constraints? And then ultimately, you know, this whole thing was going towards the notion of security closure. In other words, how do you reconcile security against the other critical things that you're trying to close today? So in summary, there was quite a bit of activities, and the goal was to, for all of this research, to feed commercial tools so that this discoveries could benefit real chip making. Anyway, now that I'm done with DARPA and I'm back in real world, and I'm forced to deal with more pragmatic problems that people actually have today, you know, my interests have sort of shifted into a different security direction. So for one, I'm thinking more about IP-centric approaches. In other words, rather than full chip, what can we do to assess vulnerability of individual IP blocks, which make up, you know, 95+% of every chip today? And then what do you do about hardening those IP blocks so that the degree of confidence is high when somebody tries to use any random piece of IP? Because today, in case of most IP blocks, people pick it up, and the first thing they do is they try to test it. Does it do what it's supposed to do? The next thing they do is they try to test what does it do that it's not supposed to do, which of course, those of you who are security researchers know that that's a thankless task. And so what one could do is use the static attestation and hardening techniques in an interweaved way to give a confidence score or trust score or something to the IP user so that they don't have to do all of this difficult and dirty work. The second thing I'm kind of interested in, and is involved in a lot of conversations in the context of the CHIPS Act, is the heterogeneous integration architecture and security in heterogeneous architectures. Principally because I think that the sub-3 nanometer chips are going to be pretty hard to swallow the huge size of this type of design. Just closing timing on chips of that size will be so cumbersome that I think there would be a logical retreat to heterogeneous integration as a dominant architectural direction. And as such, this represents interesting opportunities for security. If you have multiple chiplets, how do you coordinate security? Is there one in charge? Are they all symmetrically supporting this? And then the big one, the elephant in the room here, is the role of the interposer. Interposer is both problematic because it's typically going to be made on trailing edge technologies and thus more easy to compromise. But on the other hand, it's a unique place to isolate secrets, to maybe put portions of a key security architecture onto the active interposer. And so I'm interested in this topics right now. I think they have relevance. They're narrower than the entire security landscape. But this, I think, are some practical things that we need to jump on as a research community. And that concludes my opening statement.
Thank you, Serge. David, can you introduce your statement?
Certainly.
Thank you.
So hello, everyone. This is Dave Kehlet. And I was thinking about the topic of new frontiers. So what I wanted to discuss today were some opportunities I saw for chiplet architectures. And a chiplet, we've used these in our FPGA architectures for over 5 years now. I've got a picture in the upper right here of a main die that'd be surrounded by transceivers, ADC DAC, inline DSP. And the hardware security opportunities I see here, just number one, it's really, can we authenticate and protect IP? And the first task is can we ensure that these chiplet devices are genuine? Now, at our FPGA level, and this is true of a lot of SoCs and CPUs, they've had this kind of capability to be authenticated for 5+ years. At the chiplet level, however, this is kind of a new idea, and not a whole lot of these kind of chiplets have hardware roots of trust. So that's number one, is can you ensure that your chiplet devices are genuine? And probably even more importantly, and we might get into this later in the discussion, is you want to ensure that your firmware comes from a trusted source. And I show this on the middle right, a simple protocol to send firmware down from the developer into your base die that stores it encrypted and sends it over the chiplet, where the chiplet would test the signature of that firmware using public key encryption to determine if it comes from a trusted source. Now, this technology exists. We built this as part of the SHIP program and made it available to the Defense Industrial Base for chiplet development. And what we found is really the industry needs U.S. government requirements. On their own, there's a huge amount of motivation to go to the extra effort to provide this capability. So I'm proposing that the industry needs U.S. government requirements, and a requirement of the type such as the devices supplied to whatever program shall implement cryptographically secure authentication firmware loading. That kind of requirement. It could be as simple as a program requirement. It could be a higher level, NIST level requirement. But we need to start someplace on this, and starting at the individual program level is a good spot. And that's kind of my experience is that without that kind of requirement, developers are not really inclined to pick up the extra effort and expense of providing hardware of trust and participating in a protocol and rolling up from chiplets to a main die out to the package, the board, and so on. These capabilities for authentication and assuring that firmware comes from a trusted source. Now, the second class of opportunity I see is how can you protect IP that you have inside your ASIC? And this isn't really specific to chiplets. You could do this with any ASIC, but the chiplet architecture suggests that there might be more individual ASICs in a device than there were previously. Things that were previously built monolithically could easily be constructed now of multiple individual die. So one might say, hey, I'm going to use a general purpose FPGA main die, but my inline DSP, I have some private algorithm in there that I don't want a competitor to see, and I want to protect that. Now, in a lot of cases, certain classes of information are not able to be processed in commercial fabs. So the great news about a tool like we've developed as part of SHIP, this Ripper tool, is that you could take a design that couldn't go into a commercial fab, process it through an EDA tool, this Ripper tool, and then extract the sensitive information, IP, out of the design into a bit stream like an FPGA, and then process the resulting design silicon in a commercial leading edge silicon fab. You think of Intel's 18A process right now, we don't accept ITAR designs, we don't accept classified designs. So the motivation here is really interesting. From the defense industrial base side, they could, if this tool works as we expect, they could get access to the leading edge commercial fab. And from the Intel side, we could get access to those designs that currently go to someone else right now. So that's a great connection of the security need and the commercial need linked together there. So this Ripper tool that we've been developing, its goal is to protect silicon IP during manufacturing and test. So it's not meant to protect something during the design phase. It's not meant to protect a functioning system in the wild. Its goal is, while the silicon die is being manufactured, assembled, and tested, could you protect that sensitive IP from reverse engineering? And the technique that we've used is a redaction technique. So you actually pull out the sensitive IP, you replace the circuits with lookup tables, and that bit stream contains the sensitive IP that joins the circuit every reset or every power on, just like an FPGA. So that's the goal with this the Ripper program, to achieve this. And we've made a lot of good progress here, and we're continuing development on this throughout 2023. So with that, I think I will hand it back to the moderators.
Thanks, Dave. Murthi, did we get you up and running in terms of audio? Can you say something?
Can you hear me?
We can.
Okay, got it. Yeah, thank you very much.
Okay, so you can share your
glad to
screen
be
if you
here.
have something, or you could just talk.
I can possibly talk. I have a screen, but let me do that too.
Okay, great.
I'm trying to, but to make sure. Well, it seems to be giving me a lot more choices to select. However, I want to mess up my connections here. So let me possibly enumerate on what I have here. First, thank you for inviting me. I appreciate being called in and join this distinguished panel and the audience. My position statement is more starting with the hardware security for IoT as a compelling element for hardware security 2.0. You may call it hardware security 1.5 because it's already in prevalence and in work and is being deployed. But there has been some alarming situation in terms of security envelope across this proliferation of IoT devices at their base edge element level. My intent is to highlight why IoT as an edge, a dispersed element, is at the highest level of security concern, or based on a few things. I think all of us know about it. I just want to enumerate it in one place here so that it enhances the urgency, why it should be considered. First thing is, we have 17 billion of them out there, and they're expected to kind of go to 36 billion by 2025. They have limitless forms and functions, and therefore they provide an unbelievably dramatic expansion of attack surface for many reasons to the attack vectors, attackers on the bad actors. For example, they don't identify themselves to networks on being added, and therefore lack of visibility in networks. Therefore, they are unmonitored and unsecure device in the network. Lifespan of these endpoint units or IoT gadgets are particularly in remote industrial grade and control systems, I mean operational technology world, is about 10 to 20 years. There are up to 30% of them connected in the enterprise networks today. 98% of the IoT traffic is unencrypted. They come with default credentials, which rarely get updated, with no security patches ever particularly possible. Another thing is they lend themselves to break once, repeat everywhere, Bohr attacks of IoT devices on scale. Many have open source software, quite vulnerable to declared and listed attack scenarios. They can be attacked and weaponized for financial or geopolitical reasons, and by doing so, they can be the entry points for attacks for critical infrastructure like electric grids or pipelines by nation states, or specific targets like automotive or medical devices. Now, coming to the solution space, we don't have standards except that NIST announced just this week ASCON suite of algorithms for IoT kind of edge devices to be considered. That's a great advancement and news. But otherwise, there are no standards. There are NIST guidelines which are passed by Congress as law, but only meant for companies dealing with US government. It is not commercially enforceable. So the solution space is very splintered. It's a patchwork of consumers and industrial sector companies like HIPAA or NHTSA for either healthcare or automotive in their order. But there is no responsibility or ownership by IoT manufacturers to do anything about security needs there. So my thinking is all of these are compelling and currently prevailing magnified attack services, which mandates that IoT hardware security is a major element of hardware 2.0. And we have to remember, even something which NIST came up with, like an ASCON algorithm series of what we can adapt for these devices going forward, cannot cater to the 17 billion devices deployed already. That's a huge attack surface. Going forward, we can possibly have these algorithms in place for what is going to be deployed in future, but already have 17 billion of them out there, and many of them will be in play for a number of years. So how do you address that concern about what damage they can do or can be exploited? So these are the things which I want to see if we can bring up in today's discussion. That's my position statement.
Thank you, Murthi. Next, we'll move to Gang. Can you start your position statement?
Yes. So first of all, thank you very much for inviting me, and thanks for all the people who are online and to taking your precious time to come to this panel. And I'm going to reuse the slide set that I used the last November in a workshop associated with CAD. It is the one we call the sushi workshop, and it talk about the sustainable hardware security. And I was giving a keynote there, and then the title was given by the organizers. So they want me to talk about whether we can trust the current hardware or not. So I'm going to just, do a couple of slides to take, hopefully take the 5 minutes that I allocated to me. So first of all, to answer this question, so can we trust this hardware? And the answer was no. So this was a slide that I gave in one of the talks back 10 years ago. And I mentioned that you cannot and should not trust the hardware you are given. And actually before that, many years ago, and documented probably in 2009 when I was invited to give a talk about the role of hardware in cybersecurity. I mentioned these 3 E words: enabler, enhancer, and enforcer. And later over the years, I made these 3 words more, put more contents and then put more, fancy, figures there. And this basically tells you about what is the role of hardware in security and trust. Starting from an enabler, basically you do the things because crypto doesn't do the work. Software needs hardware to do it, and then go on to become an enhancer because hardware runs much faster than software. And eventually now it becomes an enforcer, like the one we're familiar with, the TPM, like all this, the smart doorknobs and the iris detection to identify people. So hardware now becomes very, very important for cybersecurity in general. And finally, so I want to mention about for this, for the theme of this seminar here. So this is a question I've been asked for many years. So what is hardware security? So eventually I decided to, sit down and then think about that and then came up with this phrase, and that was presented in many places in the past few years, I think definitely before the pandemic. So I define hardware security as the study and implementation. I put both words in red because to emphasize it is not just a theoretical study, it has to be practiced, has to implement. So it is the study and implementation of the protections. So protection for what? So first, the protection of circuit design and fabrication. This is something like Serge mentioned about IP. And also the protection of data storage and data processing, that is the execution, as well as the system and subsystem built on the hardware. So we talk about the IP-based design and all these edge devices, reuse of the cores and the chiplet, all these things belongs to the last category. And if you buy into this concept about these three categories, and then I would see the major problems or major challenges or potentially the future of hardware security will along these three lines. So first, it is the IP protection. I think that is Qiaoyan from the very beginning talk about this for the abstract. So IP protection is one of the very first problem in hardware security. That is more than, I think it was raised in 1996. And the second one is on secure storage and execution. And a lot of our colleagues in architecture level, they have done a lot of work. And finally, it is hardware security primitives and modules. So this you can think about, for example, there's something very known called a path. And the last slide I'm going to have here is I have a lot of things that I'm trying to see, okay, so over the years, we as a community, what we have produced. And so I'm having this timeline started from about 25 years ago and quickly go down. So you don't have to read all these things. This just shows that we as a community, we have done a lot of things to try to make this, the system, try to make the hardware, make the chips more secure and trustworthy. And as my stating point, opening statement here, so this is the conclusion slides from that talk, and I want to emphasize that hardware is the root for system. And so it is also the root for security, trust, and privacy. And with that, I'm probably going to see, I have started, hardware security a long time ago. And, but in my mind, I love the topic, but we have to be realistic. I think, the golden days of hardware security probably, but for hardware security per se, it is probably over. Think about the days when everybody was excited about the path, was about hardware children, was about, this logical locking. And now we have less people working on that. And that is not a sad thing. It is just shows it is the process of for a field to be mature. And if you go back to the old days when people study math, physics, it's the same thing. But eventually math and physics, they becomes the tool for other, science. And I think I treat, hardware security in the same way. So we have done a lot of work on PAF. We have done a lot of work on children's, on this, logic locking, all this obfuscation. And now actually it is the time that other people from other fields, they are coming, trying to pay attention to hardware security. And then it is in some sense for us to provide the tools to see, okay, what is our capability? What can we help you from system level, from software level, from social science perspective? How hardware can help these people from different layers to make their system, make their whatever, their applications more secure and more trustworthiness. So that is my point about talking about the future of hardware security. And I'm going to give it back to Qiaoyan.
Thank you, Gang. The next one will be Chip Hong. Can you start your position statement?
Okay, let me just share my screen. Hopefully I can see.
Yeah, this is on.
Okay, so I am going to keep this pretty short. So what I'm hearing from so many of the other panelists who have introduced various aspects of hardware security, probably I just briefly introduce my background. I have been more than 20 years in academia, and I want to probably introduce my earlier career research. Basically, I started with some computer arithmetic circuits, and especially on the residual number system for large integer arithmetics operation. And it turns out that the large integer residual arithmetics is the backbone for cryptography and error correction code, which is a very important component in today's hardware security and reliability and dependability. So that give me some so-called good foundation and also some chances to explore something extra, some newer field in hardware security. So my current research interests typically fall into a couple of areas. One is AI security. I think we talk a lot about Internet of Things, and also there's basically is a product of a number of technology that combine together. So recently, I think the computational intelligence form a very important aspect that drive Internet of Things in various aspects. And that can't do without sensor and sensing. So we do have a lot of heterogeneous sensors, and vision sensor particularly nominate almost all the various domains of IoT. And I think one of the challenge really is how do you actually authenticate or trust whatever sensing data, and you are basing on those to do your artificial intelligence decision and so on. So I guess there's also a lot of constraint in trying to implement security onto sensing. So one aspect is really trustworthy sensing. And I think for that perspective, although Gang have said that PUF is a relatively mature area, but I see it from the other perspective. If we probably PUF is one of the most important aspect of authenticating sensor with a lot of this environmental constraint and size and cost constraint. So what is the most important is how do we extend the root of trust or the attestation capability of PUF beyond just sensing and integrate into the artificial intelligence and computational intelligence. So the other aspect really I'm looking now quite a lot is that today there's a lot of problem that require perhaps we are quite urgent that is required to really attend to. They may not be security in nature, but they need to address the computational complexity before they can actually implement it on edge devices. One aspect is this post-quantum cryptography. So the other is that the homomorphic encryption is also one of the holy grail that can ensure integrity, privacy preservation. But unfortunately, they are really, really complex to be practically implemented on today's hardware system. So another aspect that I have seen over years is that there's a lot of emphasis on cybersecurity, and to some extent that people think cybersecurity is probably more important or have higher priority than hardware security. But one key thing I want to say is that cyberspace doesn't exist in a vacuum. All cyber systems are built using physical hardware consisting of semiconductor chip. So hardware basically is the foundation of digital trust. But the key point is it is not to be trusted implicitly. So I want to quote David Wilder, who is actually the one who invented the subroutine jump. So he mentioned that all problems in computer science can be solved by another layer of indirection, but that usually will create another problem. What is the implication of this if we look at the hardware security today is that I would think that every technology innovation are likely to introduce new security vulnerability. So for these reasons, I think people who work in hardware security have to have a mindset that attack is inevitable and not possible. So with that, I probably will open out this for discussion. So that's all I would like to say for my 5 minutes.
Thank you, Chip. So the moderators will get the ball rolling, ask a question or two, and then we'll move on to some of the audience questions. There's actually a couple in the chat already. So I'll kick it off with one question, and then Qiaoyan can take the next one. So one thing that wasn't touched on, but has been listed in the abstract, is the idea of multi-tenant cloud FPGAs. And the fact that there's been a lot of research on them with respect to side channel leakage as well as fault injection for tenants in the cloud. And it seems like this has been the limiting factor that may be holding back multi-tenancy. So my question is on that, as well as won't the same issues actually occur in these multi-chip architectures? Does anybody want to take that question?
Yeah, this is Dave. So I work in the FPGA division of Intel from Altera days, and you know the multi-tenancy in FPGAs doesn't have the same 60 years of development that multi-tenancy inside CPUs has had. On a typical FPGA, everything operates in super user mode. So developing all the access controls is a huge amount of work. And I think what we've found so far, and our customers have found, is that building a large array of FPGAs and avoiding the multi-tenancy problems is a more practical near-term approach. You know, eventually I could see it happening. It's enough challenge right now to keep a single tenant from causing trouble inside an FPGA by accessing protected pieces of hardware such as reconfiguration and those sort of things.
So I would echo what Dave said. Domenic, you floated this topic earlier, and it sort of threw me for a loop because I was unaware of existence of this problem. So I asked around people who work with the cloud on a daily basis, and basically came to the same observation that Dave just articulated, that this problem may exist in the future, but right now does not.
Yeah, maybe I just add on. My personal opinion is that multi-tenancy FPGA, it's probably not because of the security that make it less popular. I guess there are two aspects. One aspect is the problem with the reliability, because the data corruption can propagate through all the clients in an instance, and maintenance, downtime, and service update also affect all the clients at the same time. The second aspect is really the user experience, because the performance cost imbalance is really difficult to assess in a multi-tenant situation. That is because most of these multi-tenants, there is two aspects. You can actually virtualize the computing resource, but there's difficulty to virtualize the communication. So that causes some communication intensive application, which may run worse than the computation intensive application on a multi-tenant platform. So that's and second thing is that the user might have difficulty ready to assess this performance on a multi-tenant situation. So they really do not know what they pay for and what they actually get out of that, whether it make a good balance of this, because most of this today's this virtualization is actually based on the CPU or memory virtualization. It's not based on FPGA resources virtualization for the estimation tools. So from this perspective, I guess it's, although there are security problems, but that probably is not the main so-called things that discourage the use of the multi-tenancy FPGA.
Yeah, so I agree with Chip Hong. So a multi-tenant FPGA could be a very brilliant thing for the future. And as Serge and Dave have mentioned, probably it is not right now. And even if there's some technology issue that is holding it, it is probably not the security issue for now. And I know that within academia, there are quite a few places, and then people are working on the security and the trust issues about multi-tenant FPGA, in particular FPGA. So I think that is a nice effort. It is much better for us to study the problem before when it comes to the market, everybody's using it, and then we find all kind of problems.
I want to take a position in a business sense, apart from the security aspect of technical aspect of security and all. It may be the customer resistance. For example, it may be the mindset of a business customer community currently contracting with renting compute time or resources with this cloud server farms. So they have to first get comfortable with. If I'm a businessman, if my design or my workload is coexisting and cohabitating in the same FPGA with another application, which is unknown and therefore trust deficient, any potential loss of proprietary information is an uncomfortable thing for me to agree to such a proposition. Yes, for the AWS and other server farms, it is a great resource benefit. But as a customer, I may have my own limitations about agreeing to that. Now, because for the cloud hosts, even those who have the server farms as a business model, the liability factor, if a security mishap should occur, and along with any subsequent business brand name hit, is an enormous hurdle to overcome for very eager adaptation to multi-tenancy. And of course, then there is always the technically driven zero-day possibilities, which they cannot account for control, is also a concern, because again, with the possible damaging outcomes mentioned above.
Thanks,
Right.
everyone. Qiaoyan, do you want to take the next question?
Yeah, thank you so much, panelists, to give us a very important views. Another question we have like here, like Gang show, the golden day maybe for hardware security may be gone. Then what's the most pressing threats that the hardware security should focus on right now as a short-term goal, and like less than 3 years, or for the long term, like the next 10 years, what was the pressing need do we need to consider for hardware security community?
So since you mentioned my name, so can I start?
Sure.
Yeah, so when I see the golden days are past, it doesn't mean that hardware security is not an area to work on. It is still one of the most promising area for across the security, domain. And what I'm saying here is actually, we should not restrict ourselves to EDA problems anymore. We should open our mind, open our eyes, and like Chip Hong mentioned about, for example, AI security, about biometrics, about postal quantum. And all these things traditionally they are outside EDA, but the things as what I'm saying now is, so for hardware people, now we should try to get out of our comfort zone and really looking for new opportunities, looking for new applications. And I mentioned hardware, and also I think Chip Hong also mentioned hardware is the root of everything. You cannot go without hardware. And if you're asking about the next year or next 3 years, I think this favor of AI, machine learning, it will stay there for at least 3 years. So that you see a lot of things on this AI machine learning accelerators. And then people talking about this, I mean, recently this ChatGPT things. So a lot of things will probably can be related to hardware. Like, for example, I mean, you have a ChatGPT account and then you are using that and they are going to trace you. And then they may have hardware, I mean, components that can help them to do that, or you can use that to try to, in some sense, protect your privacy. And also people have done many years about, for example, on this federated learning that is also related, I mean, to hardware. So a lot of things people don't think it is hardware is getting involved, but hardware is there. And back to this multi-tenant FPGA or cloud computing thing, I think that is also a good area to work on in the next 3 years, 5 years. And so a lot of new things. You just, I mean, in some sense, need to open your eyes and then just don't say, okay, I'm going to work on circuits. And also, if you want to go down, we talk about the. I think there's a question in the question and answer part about the post more. I mean, computing here. So we talk about the processing in memory. We talk about the neuromorphic computing, and so all these areas. I think there will be new challenges and new vulnerabilities from security perspective. Yeah.
I'd like to chime in briefly. I would say that as far as near term is concerned, and I don't know how much things have changed recently, but as of a year ago when I was in the government, it was and looked at security issues. Basically, the economic attackers were the most dominant presence on the landscape, and they typically attack systems that are as close to the money as possible. So attacks on the smart cards, attacks on set-top boxes, and there's a whole industry that's sort of come together to attempt to defend those things. So I would say that probably continues to be like a most visible and near-term kind of attack, not to mention the IoT devices that came up earlier that create a huge attack surface. And for terrorists, it may be quite gainful to attack kitchen appliances if they could cause substantial damage if they successfully exploit that weakness. I would say in mid-range, mid-term, reverse engineering from the nation state perspective, I think is an interesting attack vector. But here with a slightly different focus, not trying to necessarily reconstruct the netlist, but rather intercept data in motion and data at rest and infer from the data what is actually going on, not for the purpose of cloning the design, but for the purpose of understanding the algorithms. And then in the longer term, I really do believe that heterogeneous integration platforms are going to be extremely compelling and will become very, very popular. There's going to be lots of companies that will rush solutions to market based on heterogeneous integration and completely ignore the new attack surfaces that architecture exposes.
Sure.
And so I think 7 to 10 years from now, when heterogeneous integration platforms will be common, we will be talking in one of these forums again how easy those things are to attack and why hasn't anybody thought 10 years ago about creating a more secure architecture. And the last thing I wanted to note is you mentioned ChatGPT, and that's a very interesting attack vector as well. You guys probably know that when you go to commercial websites, they track how much time your mouse hovers over objects, and they construct a very accurate model of you as a consumer based on what you click on and what you hover over. Now think about how much you reveal with your questions to ChatGPT. I mean, a much more accurate model of a human can be constructed based on your now verbose dialogue with the AI system. So I think Gang actually mentioned this. This is a very interesting point to focus on. We are going to be voluntarily sharing a lot of insights about ourselves, and how do we anonymize this somehow? What are the layers here? Maybe this becomes more of a software or AI problem rather than a hardware problem. But I think it's an interesting one. I mean, right now companies spend a lot of effort to figure out what you're likely to click on next. Here, you're just telling them what you're interested in and what you want to do.
This is Dave. Maybe I'll chime in here as well. On the heterogeneous integration, you know, that drawing I showed there, it's got GlobalFoundries 12, it's got TSMC 16 as Intel 7, all inside a package. And the driving force is that you can get the best out of each of these processes. You know, a high performance digital process might not be the best for photonics, for example. So I think that this is driving these new attack surfaces that you have with these individual chiplets being assembled into a package. And I think in the short term, you know, all these chiplets have microcontrollers in them to perform calibration, to perform other operations. And, you know, an attack may not be to disable these or steal the IP, but it could be simply to, you know, have a DSP ignore a certain band of frequencies when it's processing data, and therefore make an attacker, a physical attacker, invisible. So I think that in the near term, you know, protecting the firmware that goes into these things. You folks remember that the Stuxnet attack from a dozen years ago. If those Siemens microcontrollers had authenticated the firmware came from a trusted source, the attack would not have happened the way it turned out. So that's the number one thing I would think in the short term is really focus on making sure the firmware that goes into these hardware devices comes from a trusted source.
I will pitch in again. I'm sorry, go ahead.
Yeah, so let me just share something I thought would be probably quite different from the current landscape. I think we are quite used to the CMOS technology that is basically a subtractive manufacturing technology. So we probably have to start thinking there are increasingly interest, and in fact they have already go into various biomedical device, electronic skin, even this transparent label and so on. So that particular technology is printed electronics. It is very different because it is additive manufacturing. Second thing, it can also be manufacturing or it can be printed on site at the user site. So that size of the footprint and also the substrate, it can be paper, it can be textile, and second thing is very low cost. So I think it will probably rule out our thinking on conventional, including your IP protection and so on this particular type of manufacturing technology, and it actually is not going to replace, but it's going to be a complement of the current CMOS in some applications. So already it will bring in a completely different trade landscape that is worth many of us to start looking at that and thinking about this. I wouldn't think this is a short term, probably it will be a long term, because there will be a lot more new material for this and new possibilities of printing this printed electronics. So there's one angle on this that is quite different from where we are doing currently with this IC manufacturing technology. Yeah.
Thank you. My pitch for the next 3 years is again my pet topic. I talked on my position statement. I don't want to elaborate too much again on that. It's just that urgency of it, given the enormous and enticing attack surface, a threat surface created for the hacker community, begs for a solution near term. I've already seen that there is an inflection point from ransomware and other attack situations which happened for the last couple of years, now pivoting to the IoT domain, just because of the enormous opportunities available for the bad actors. So near term, I'm hoping that there will be increased attention to address this already deployed problem.
Hey, thank you, everyone. So we'll go to some of the audience questions. So we have quite a few of them here. So Qiaoyan and I will probably choose one or two, and then we'll go to the panel's closing statements. So I'll try to choose this based on what's been discussed and what hasn't been discussed. So I'll choose the first question from anonymous attendee, and that's, will hardware Trojans still be a significant threat after the CHIPS Act?
So your question was the intersection between security and CHIPS Act. Is that the question?
This one is specifically about Trojans and the CHIPS Act.
I'm not. I've read all the CHIPS Act docs. Maybe I don't recall it, but there are several places where security is prominently mentioned, but Trojans specifically, I don't recall. So there is there's in microelectronics commons, there's a lot of talk about secure edge. In NSTC, there's a topic of heterogeneous integration security, and in the metrology component, there is the secure supply chain management aspect here. But I maybe somebody else had seen it, but I have not seen mentions of Trojans. Maybe because they're just not commonly found in the non-classified space.
Yeah, this is Dave. Just looking at the question here, it says, you know, since we assume most of the chips will be manufactured inside the U.S. So I think that the question is saying, you know, given that they're made inside the U.S., does that reduce the risk of Trojans? I don't think it fundamentally changes the picture. It does mean that it might be harder for certain actors to do it, but I don't think it fundamentally changes it.
Well, if for Trojans inserted during manufacturing, yes, but you still have the untrusted employee or compromised employee attack vector, and certainly you have Trojans embedded, where Trojan trigger and payload are embedded in the IP block. That doesn't, domestic manufacturing doesn't do anything for that.
Yeah, that is absolutely correct. So this CHIPS Act probably helps about the manufacturing, but you are using EDA tools, you are using third-party IPs. So that doesn't help for hardware Trojan.
Also, I can see that there is another possibility that a malicious effect is built into an hardware, but it's probably not directly through Trojan, but it's through some form of backdoor. Particularly in AI, you can actually poison the data, and then somebody unconsciously trained this poison data set. They build a hardware. The model is poisoned, so the hardware also carry this malicious so-called feature, which although it's not called a Trojan, but effectively is very similar to a Trojan. It can be activated in the field. So I think if we don't look at it from the narrow angle of Trojan has to be insider, I think there's a lot of possibility. You can be through the EDA, you can be through the model construction, can be through third-party synthesis and design tools. I guess there's a lot of channel beyond just manufacturing.
I just want to make a general observation that given the wide knowledge proliferation and widely dispersed how to catch and defeat an embedded Trojan, my thinking is there'll be ways found to insert one if it doesn't need to be ordained into the manufacturing domain. That's where the CHIPS Act comes into play, as others have said here. For example, I had tried JTAG as my entry point, knowing the safeguards which have been put in more recent years, how to restrict that entry port to be a vehicle to get in. So the very knowledge of what is being put in as a mitigation or a countermeasure, since it is so open knowledge and widely dispersed, will help for more sophisticated Trojans to be coming into play. So the Trojan domain outside the fab sphere is very much alive, and therefore there is no expectation that it will come down in any way because of the CHIPS Act. Over.
All right, thank you all for the answer. I think audience already received enough message from all your comments. So let me move to the second question I randomly picked. The question is, does the security for IoT device have to take place at the hardware level or device level? It's easy to conceive that many small companies who will be destroyed by legislation requiring them to provide the security. I think the question may ask for the cost. I think transfer our knowledge from the research perspective to the practical use.
Let me take a stab at that. Since I was talking about IoT, the solution space spans across different domains. If you're looking at something like a public key kind of offering or a solution, obviously you cannot put that kind of technology inside a edge point sensor. So you have to see if there is aggregation of a secure solution available. For example, in this case, if you have widely dispersed sensors in an industrial environment, you might want to look at a solution at the gateway point, because obviously it's a lot more easier to update or with the firmware fix or anything at a gate level, single gate level, instead of maybe 1,000 sensors it's connected to. So it depends on where you position the solution you want to bring up, commensurate with what the devices in play can handle. So obviously for anything which is small form factor, sensors or endpoint gadgets, you may have to let go of too much heavy compute solution. But for other aggregating points, you may think of a solution which is adaptable. So you have to be picky and choose and do it in a smart way.
I would comment that I'm not aware of the regulation that the questioner is asking about or referring to. Maybe there is one or there isn't, but if there is in fact a regulation of some sort, it takes a lot of effort by the government to actually put that into practice and a lot of time. And so to me, even if there was some legislative or regulatory security requirement, it's not at all obvious that it'll actually make it to consumer devices anytime soon. In DoD, when I was there, we had there was a regulation about security for silicon going into defense systems, and it was largely ignored by the defense industrial base. So the strength of this regulatory regime is always in question. On the other hand, I have seen lots of IoT startups. They completely ignore security, and because their primary concern is time to market. And they invest a lot of energy into the so-called eye candy, which is their smartphone app that controls their thing. There's almost like an active resistance to security in that community. So if there was in fact regulatory regime that was effective, I think it would be a good thing if it applied to everybody.
Yeah, this is Dave. So I think that the argument about legislation here is kind of like the argument against seatbelts. You know, on Serge's DARPA Shield program, the device was 100 microns on a side. So this can be very, very small. The cost of the IP can be very, very minimal. And so I don't really think that this is an impediment. It may not be a focus of a company's actions, but providing the security, I don't think is much of a burden.
Dave, I'm glad you mentioned Shield. The interesting thing I've learned is that the Shield cost target was 1 cent. So this dial was supposed to be targeting 1 cent cost, and it was met. But when I tried to market it outside of the defense community, the commercial parties thought 1 cent per item was way too expensive. This is like people who sell ladies' handbags for $6,000. They thought 1 cent was too high, or rare wines that cost. So it's quite interesting. There's a book that I read a long time ago, and that was like talked about the difference between something being free and something costing 1 cent, and there's a huge customer psychology theory behind all of this. So you would take a free item even if it was hugely economically disadvantageous to you. I agree with Dave's observation.
Just one observation I want to make. Most of the time, the enforcement comes from a business needs. For example, in fintech, the payment card industry, security standards came about by amalgamation of these big four credit card companies, Visa, MasterCard, Discover, and American Express, because cash transactions inherently need secure guardrails. Similarly, in the auto industry, there is safety standards, ACL-D through ACL-A or ACL-QM. And since given that no safety can be there without a security envelope around it, so it is possible that the automotive industry will step in and give for mission critical needs, come up with a level of assurance LOA 1 or L2 LOA 4. So the auto industry might play a big role. And for supply chain management and security assurance, the insurance industry is well positioned to demand secure supply chain link from the key stakeholders in a global supply chain domain, because no other entity has the enforcement power across a global chain to make it mandatory. Well, military aero command is security is somewhat defined. As I heard, it is not enforced. But again, these are not in high volume, so I don't think the commercial industries will be so much bent. The hardest one is the CAD supply chain, which is across everybody and gets to use it. Maybe they fall under many of these other items I just mentioned, where enforcement can be driven by business needs, and hopefully that's how the compulsion or the need for it is enforced by the right entities.
So let me, come back to talk about the first part of the question. So does security for IoT devices have to take place at the hardware level? So I think this is a great question, and I think the answer from the panelists, it is yes. And I think, so sorry if I pronounce your name incorrectly. So says Yamashi, and you mentioned about this the public key cryptography. So you cannot afford to do that on edge devices, on IoT devices. So this is indeed a perfect example that hardware security people, we can work on. So instead of using the traditional crypto, you can use something that features the hardware perspectives and use that to provide something within the research community we call the lightweight crypto. And one of the example is how can you utilize the underlying hardware features to provide, for example, authentication, authenticate the device, authenticate the person, and also trying to provide the data integrity, these kind of things, which traditionally are protected by crypto algorithms, but edge devices, IoT devices, they don't have the power, they don't have the energy, they don't have the computation power to do that. So it is a good question, and I think it is a great area to work on.
Yeah, I probably want to add on something quite interesting observation, that is that I think security, quality and security feature, unfortunately, is something that cannot be easily identified by the customer. So customer will be unwilling to pay a premium for that feature that they cannot identify. So this is very, there's a economy concept called market for lemons. Because of this, they use a used cars market as an example. So if the product quality is unobservable by the buyer, then the seller will try to lower the seller will try to lower the product quality, and then buyer actually expect the seller to skin on quality, and then they are unwilling to pay. So in the end, the price will decline, and the seller are forced to lower the quality first to make the profit at a much lower price. So this market for lemons phenomenon actually prevent those with the ability to solve the problem from doing so. So really, it's really important really to achieve measurable security outcomes, to make security an asset, not just a necessity. So I guess this is one thing that could actually help transfer or adopt certain research outcome from the security community to the practical use. I hope this is a personal opinion, but it's somehow related to consumer psychology.
Thank you, everybody, for answering that question. So we're running low on time. I want to make sure I give the panelists some time for closing remarks. So maybe 1 to 2 minutes per panelist based on what was discussed and what questions came up. And we'll start again in the way they were introduced. So Serge, can we start with you?
Yeah, so I didn't know I'd have an opportunity for closing remarks, so I'll be going right off the cuff here. So I would say that I really enjoyed being submerged into hardware security community for 4 years when I was in the government, and found a lot of brilliant people doing original research as well as building on last 20 years of other discoveries. I think my thought is the time has come to consolidate the discoveries from the last 20 years into meaningful solutions. So in other words, I'd rather see people integrating multiple security strategies to solve problems that we discussed here, as opposed to inventing more puffs, for example, which so I would say that there's been a burst of research in the recent history, and time has come to sort of consolidate the discoveries and focus on things that are useful. And to me, the most pragmatic low-hanging fruit right now is, all the chips being designed are largely made up of reused IP. 90%, 95% of most designs are IP that's either legacy IP from their own company, open source IP, commercial IP that's commoditized or differentiated commercial IP. And so I think this should be the area for security focus. That's where intentional and unintentional vulnerabilities exist. This is where you can vary triggers and payloads. And also, I think this is something that has economic cost. When any piece of IP you pick up, you intrinsically distrust, and you spend a lot of time that could otherwise be spent on productive endeavors in verifying that this thing can in fact be trusted. So I think that there's a pragmatic thing that the research community could turn its attention to in the near term, which is, we are swimming in the sea of IP. How do we improve the situation so that IP can be used out of the box with as much confidence as possible? And also, going along with that, is there a quantifiable way to express trust and the confidence? Is there some kind of a trust score? Is there a security score? Is there some objective metric that people can look at and say, oh, this is trustworthy? I personally don't like the word trust in this context, but something like that. So that's kind of my closing statement and call for action.
Thank you, Serge. Next, Dave.
Yeah, I think the discussion about the economics of hardware security is really interesting, and I really appreciate the questions and the panelists' view on this. I think the big targets, like the kid who hacks into a Tesla, those things will naturally have kind of their own economic reasons for implementing security. An official in the U.S. government, when I was talking to him about supply chain security, said it was essentially a boil the ocean problem, that it was hard to get the whole thing done, and who was going to pay for the system, who's going to pay to maintain it and operate it. So I think the solution is we got to get started someplace, and let's get started maybe bottoms up at first on this. Things like as I mentioned, providing cryptographic authentication of devices, and ways of determining the trust of your firmware supplier could allow us to incrementally get towards a supply chain security solution.
Thanks, Dave. Murthi, how about you?
Oh, hi. So looking at the economics and the time to market aspects of it, obviously those still keep the security as an afterthought, much after the design is done, it's deployed, and when a breach happens, it's more reactive. That's when things show up in the news. So obviously that is not the approach which will sustain. It's sustained so far, but I don't know if it will going forward, just because of the attack surface is growing bigger. So there has to be some kind of an enforcement-driven motivation. No business wants to expend resources and time and money unless they cannot do business without it. So there has to be some enforcement regimen across different industry sectors, which require these things to happen. For people who say for sensors, kind of edge point devices, it is an economics issue. I essentially agree, but the NIST and the academic world are coming up with improved, lightweight, implementable algorithms. The recent one is ASCON, which got released this week. So there has been a push towards for solutions on the technology side. Now the question is, what will motivate a businessman who creates these gadgets and manufactures them for obviously business purposes and profit motive being there? How do you have that enforcement? And how do you do that across the global chain? I mean, many of these products are globally linked in terms of supply chain. How can you pass laws and enforcement which are there in the United States? But then how do you have that requirement met outside the offshore locations? So those are the aspects which need to be considered while technology keeps its pace. And I hope the forums out there will address those.
So is that my turn? Yeah. Okay. So first of all, I think, when I look back, I think we as a community, we have done a lot of things in the past, probably 20, 30 years. And just to think about this, so now we can get 100 people online, listen to this webinar. And then this is something you can never think of back 20 years ago. And over the years, we as a community has, first of all, made it the normal people be aware of the security vulnerabilities of their hardware of the device. And also we have built a pretty solid foundation about examine the vulnerabilities of the design process, the manufacturers all the way to EDA tools, IPs, and then trying to identify whole kind of potential security threats there. And we have built countermeasures. We have built a security, I won't say security metrics, but security methodologies, so you can make your design more secure, more trustworthy. And back to this webinar's title, talking about hardware security 2.0, I think this is probably a right time for us to look forward and then to see, okay, so how can we make the impact bigger? And we know that, I think it is probably Serge what Dave mentioned about eye candy. So we're developing hardwares, but we're not developing eye candies. But eye candies are the features that capture people's attention. So it is up to all of us trying to apply hardware security and then try to take this to the broader community to see at hardware level what we can do and what are the potential, vulnerabilities if you don't pay attention to security at hardware level. So I think that is probably one of the key things. I hope everyone can work together so we can grow the community bigger and then make more impact.
Thank you, Kang. Chip?
Yeah, I agree with what Kang said, but I want to highlight a couple of points. One thing is that I guess the skill workforce is one of the important, or currently is probably also a weakest link. If we have really more security skill workforce, then probably that will push a lot more awareness. But anyway, if you compare with when I started looking at some of the hardware security, at that point of time, the awareness is actually quite poor. And today we are in a better position. So the optimistic part is that with this level of awareness, any new technology, when they start to look at the standard, for example, the interposers and all this, they will probably incorporate security and hardware security into consideration, which is quite different from the older day. I think this shared some similar trend as the clean energy. Initially, there's a lot of reluctance because of cost and manufacture, but as things get more serious, I think there'll be more inclination and more encouragement to take on security as a upfront consideration. I think I would like to look on the bright side of this. Yeah.
Yeah, thank you, everyone. I'll give an opportunity for the organizers in a second if they want to say anything. But first, I want to thank obviously the organizers for putting together the panel and giving Qiaoyan and I the opportunity to organize it. And I want to thank the panelists for all their interesting takes on the questions. Thank the audience as well. And finally, I want to thank Amanda and Bailey for the support in organizing the event as well. Swarup, did you have anything you wanted to add?
Hey, on behalf of the organizers, we really appreciate your effort and help and support, Domenic and Qiaoyan. And one more time, thanks a lot to these distinguished panelists. I think the panel has been exciting. A lot of knowledge to take home from this panel. So that's great. I guess the audience has also enjoyed it. Thank you everyone who attended this event. As I mentioned before, this is recorded and the recording will be available soon. And I would also thank Amanda and Bailey for their excellent support and everything they have done behind the scene. And they were always great help. So thanks for your continuous support and help. And IEEE CEDA, HSTDC, thank you very much for your continuous help and support. So we'll see you all in the next event. Stay tuned. We'll make the announcements for the next panel and few more webinars. Yeah, back to you if you have any parting comments.
Thanks. Not much from my side. So I would like to thank all attendees and especially our panelists and moderators. Thank you.
Bye, everyone. Thanks.